Hello, I'm going to talk about optimal order regret bounds for kernel bandits. Let's see a formulation of the problem. There is a decision domain X, an objective function F, and a learner or decision maker selects a sequence of observation points from the domain X1, X2, and so on, and receives the noisy observations Yn, where here this epsilon n is the observation noise. And the objective is typically to minimize the regret. That is the difference between the optimum point for f. So this is the maximizer of f minus a candidate maximizer output by the algorithm. So sometimes the performance of an algorithm is measured in terms of cumulative regret. That is the sum of such terms over this trajectory of observation points from 1 to n. But for this presentation, we focus on simple regret. So there are two main assumptions. The first assumption that is that f belongs to a reproducing kernel Hilbert space of a known kernel K, or more precisely, the RHS norm of f is upper bounded by constant B. And the second assumption is that the observation noise is sub-Gaussian. For algorithm design, it's useful to employ a surrogate Gaussian process model, which provides us with a mean and a variance. So these are the standard posterior mean and covariance of a multivariate Gaussian, given the observation points xn and yn. So this is one important building block in the analysis. The confidence intervals for the RHS elements with sub-Gaussian noise. So provided n observations, where the observation points are independent from the observation noise, we have this confidence interval for the RHS element. So basically, f, the difference between f and prediction provided by the surrogate GP model is upper bounded by a factor of the standard deviation. This confidence interval width multiplier is the summation of the upper bound on the RHS norm of f, the first term, and a beta delta term, which is given here at the bottom of the page. So from this figure, we can basically see this solid blue line is the prediction provided by the surrogate GP model plus minus a factor of a standard deviation basically determines our confidence interval at each point. Consider a simple algorithm referred to as maximum variance reduction, where each observation point is selected as the point that has the maximum uncertainty or variance based on the prediction provided by the surrogate Gaussian process model. This is a natural way of selecting points. These are basically the points that have the highest uncertainty, so we would like to choose these points to reduce the uncertainty. And after selecting n points, the candidate maximizer of f is chosen based on the prediction provided by the surrogate GP model. So for this algorithm and using the confidence intervals given in the previous page, this paper provides this theorem, which says under the regularity assumptions which we discussed with probability at levels 1 minus delta, the simple regret of this black box optimization problem is upper bounded by a square root of gamma n divided by n. So this gamma n is a complexity term that is kernel specific and independent of the observation points. And the next slide, we will take a closer look at gamma n. So this gamma n is the maximal information gain. That is, let's say I is the mutual information between the observation points and the underlying surrogate GP model, which for Gaussian processes, we have a closed form expression for I given here. Then this gamma n is the maximum of the mutual information over all possible sequences of observation. A second component in the analysis of the black box optimization problem is upper bounds on gamma n. So this paper provides improved upper bounds on the maximum information gain compared to the existing work. This table provides a summary of the results. The bounds on the information gain depend on the eigendecay or the decay of the eigenvalues of the kernel. So we can consider two general cases where the eigenvalues decay at a polynomial rate, then the upper bound on the information gain has a polynomial dependence on the number of observations. And when the eigenvalues decay exponentially, the upper bound on the information gain is logarithmic with the number of observations. We can also see a specialization for two cases of Matern and squared exponential kernel, which are the most popular kernels in practice. Recall the regret bound. We can replace the values for gamma n and obtain this specific regret bound in the case of Matern kernel with parameter nu. This is order optimal up to logarithmic factors when we compare it to the lower bounds provided in this paper. And in general, these results can be extended to the cumulative regret. For example, see this recent paper. Thank you.